Let us look at the fundamental spaces that are induced by a matrix, and which will bring us to the singular value decomposition. So let us say that there is a matrix A which is m cross n and has real entries. Then the range space of A is denoted, so it is a set and is denoted by R of A. So this is defined as the set of all vectors in Rm such that these vectors can be written, each of these vectors should have been written, or we should be able to write these vectors as A times U. Right? In order for this multiplication to be valid, obviously we would require U to be in Rn. So because only n cross 1 vector you can multiply with A. So this is the definition of the range space of A. It is also called the column space of A. Right, so that is another name. And this essentially is saying, so what is it saying? It is saying that you can write V, which is an element in the range space of A, as a linear combination of the columns of A. So this is saying that you can write it as U1 times A1. So A1 is a column of A, plus U2 times A2, and so on till UN times AN, because there are n columns of A. So you can linearly combine all those columns and the sum will be an element in the range space of A. So range space of A is constructed by taking the linear span of the columns of A. You must have seen this notion that this range space of A is a subspace. So that is to say that if you have two elements, so let's say V1 and V2 are two elements in R of A. Remember that V1 and V2 are vectors of size m cross 1. If there are two elements, this would imply that there exists some U1 and U2 such that V1 is equal to A times U1 and V2 is equal to A times U2. Then what can you say about the linear combination of V1 and V2? So if you say alpha 1 V1 plus alpha 2 V2, then you can check that the linear combination can be written as A times alpha 1 U1 plus alpha 2 U2. Right? So alpha 1, alpha 2 are scalars. So then this kind of expression is possible. So this means, so what does this mean? That this quantity, which is the linear combination of V1 and V2, also belongs to the range space of A, because it can be expressed as A times some vector in Rn. So therefore alpha 1 V1 plus alpha 2 V2 is also an element of range space of A, and hence R of A is a subspace. So subspace is, linear subspace is any space where all the linear combinations of all its elements also belong to that same subspace. The dimension of R of A, right? The dimension of R of A is basically the number of linearly independent columns of A. So in other words, if you remember that RA is being expressed in terms of columns of A, so if all of them are linearly independent, then that would be, n would be the dimension of RA. So in general, it is the number of linearly independent columns of A. This is, by the way, also called the column rank of A. This is also called the column rank of A. So in the same way as we have defined the range space of A, the other fundamental spaces of A can also be defined. The null space of A, so NA denotes the null space, is defined as the set of all vectors u in Rn such that a times u is equal to 0. So all vectors that multiply upon multiplying with a give 0 forms the null space. And then finally we can have the range space of A transpose. So range space of A transpose, so that is R of A transpose, and we can define it in the same way, but I will just use a slightly different notation, and the reason for that will become clear. So this is a set of all u in Rn such that u can be written as A transpose times V. Now V is in Rm because of the size of A transpose. And then finally we have the null space of A transpose, which is N of A transpose, which is the set of all V in Rm such that A transpose V evaluates to 0. So these are the four fundamental spaces associated with the matrix A. So just to recap, you have a matrix A, we have the range space of A transpose, the null space of A transpose, null space of A, and range space of A. Right? Remember that elements of range space of A were in Rm and elements of null space of A were in Rn, and likewise the elements of range space of A were in Rn, A transpose, and the elements of null space of A transpose were in Rm. Right? Now let us look at all of these in slightly more detail, which is that how they are related to each other. So let's say that there is a vector W which is orthogonal to the range space of A. So what does this mean? What does this statement mean? It means that if you pick an element of A, Ra, then that element is 90 degrees with W. So this statement is equivalent to, this is a sign for equivalent to W transpose times an element of Ra. Remember that an element of Ra was of the form AU, right? So W transpose AU is equal to 0. So this was V, which was in Ra. So an element of Ra was of the form AU. So W transpose AU is equal to 0. And this should hold for all U, because all elements of V can be expressed as A times U. So therefore this should hold for all U. So what does it mean? What does it mean for W transpose AU to be equal to 0 for all U? So let me rewrite it in a different way. So it is essentially saying that U transpose times A transpose W is equal to 0 for all U. So A transpose W is a vector, and we are saying that this vector is orthogonal to U for all U. So no matter what U I choose, this vector is always orthogonal to it. This is not really possible unless this vector is 0. So this statement is exactly equivalent to saying that A transpose W is equal to 0. So only when A transpose W is equal to 0 can this product be 0 for all U. Right? So this means that, what is the meaning? It means that W belongs to null space of A transpose, because this is exactly the definition of null space of A transpose if you look at the top. Right? So in other words, we have established that the range space of A, orthogonal, any element that is in the orthogonal of range space of A, is exactly in the null space of A transpose. And likewise, we should be able to establish in the same way that the orthogonal space to null space of A is the range space of A transpose. Right? So this is the relationship between two of the spaces, two pairs of spaces. And then one more property which I am sure that you are familiar with, which is that the rank of A is the dimension of the range space of A, and it turns out this is also the dimension of the range space of A transpose, right? So this is what we call R, and it has to be less than M and N, both less than equal to M and N. So now, having defined the four fundamental spaces and having related them, let us look at the singular value decomposition. Just to summarize, remember that we said that the elements of RA are in Rm. So let's say Vi is in Rm. Then how many such elements are there if we want to express them using an orthogonal basis? So let's say V1, V2. So there are R such elements because the rank of A is R and the dimension of RA is R. So there are R such elements which are in RA. And the rest of the elements, where are they? So VR plus 1, because V is a m cross 1 vector, and there are R elements, so the remaining elements R plus 1 to Vm should belong to null space of A transpose, right? So these are the elements that are all orthogonal to range space of A. Remember that null space of A transpose is exactly the orthogonal of R of A, right? So R of the elements are in RA, and the remaining elements which are all orthogonal to this are in null space of A transpose. In the same way, if you say that Ui is in Rn, then there are n cross 1 vectors and there are n such vectors. So out of those, U1 to UR are in range space of A transpose, and the remaining ones, UR plus 1 to UN, there are n such vectors in this case, are in null space of A, right? So if there is an n dimensional space, there are n orthogonal bases. R of them would belong to range space of A, remaining would belong to null space of A transpose. Similarly, R of the vectors in n dimensional space would belong to range space of A transpose, and the remaining would belong to null space of A. So this brings us to the singular value decomposition. So singular value decomposition is basically always possible for any rectangular matrix, and it basically relies on extracting these components V1 to VR, VR plus 1 to Vm, and U1 to Un. The singular value decomposition of a matrix A is given by, so you get V1 to VR, VR plus 1 to Vm. So there are m such vectors on this side. All of these are columns times a diagonal matrix of containing sigma 1 to sigma r and rest zeros. So it has only the first r diagonals which are non-zero, times u1 transpose till ur transpose all the way to un transpose, right? So these are all rows. If just to recall, this is R of A, this is the basis vectors for null space of A transpose, this is the basis vectors for R of A transpose, and these are the basis vectors for null of A. And also to recall, this is an m cross m matrix because VIs are in Rm and there are m such vectors. This is a n cross n matrix, and this middle one is a m cross n matrix. And in the same way as eigenvalue decomposition, we can also express this as sum of several rank 1 matrices. So this can be expressed as sigma 1 V1 U1 transpose plus sigma 2 V2 U2 transpose, so on till sigma r VR UR transpose. right? And by convention, all the sigma i's are strictly positive. So in this case, it is always possible to arrange it in this way. And you can always pick the basis vectors such that sigma i's are all strictly positive. Note that this decomposition doesn't really depend on Vr plus 1 to Vm or Ur plus 1 to Un. So this decomposition does not really depend on these two parts. So this is just for our convention that we have added these. And if you calculate this, you can calculate it in such a way that you don't need to evaluate these parts, null space of A transpose and null space of A. So you can just directly calculate sigma 1 V1 U1 to sigma R VR UR, and that is sufficient. And if you want to calculate it fully, then that is also possible. So MATLAB, for example, allows both forms. Now to conclude, let us see the link between singular value decomposition and eigenvalue decomposition. So what is the link between singular value decomposition and eigenvalue decomposition? So let us say that there is a matrix which is M cross N. So let the singular value decomposition of A be given by A is equal to V sigma U transpose. So if you look above, V is the first matrix, sigma is the middle matrix, and U transpose is the last one. And we know that because these are orthogonal basis vectors, we know that V transpose V is identity, and likewise U transpose U is identity. V and U are orthogonal matrices. Then let us calculate what A transpose A is. So A transpose A is given by U sigma transpose V transpose V sigma U transpose. Now if you remember, we said that this is identity. So this becomes U sigma transpose sigma U transpose. Now what is sigma transpose sigma? If you look at the structure of sigma, then sigma transpose sigma is nothing but a square matrix containing sigma 1 square, sigma 2 square till sigma r square, and rest would be zeros, right? And now you can see that this looks exactly like an eigenvalue decomposition, right? So this looks exactly as U times sigma transpose sigma times U transpose. So this is your eigenvalues. These are the eigenvalues, and U would contain the eigenvectors, right? So in other words, the singular value of A square is exactly the eigenvalue of A transpose A for I equal to 1 to R, where R is the rank of A, R is the number of non-zero singular values of A, and it is also the number of non-zero eigenvalues of A transpose A. So this is the link between singular values and eigenvalues. Note that a similar observation can be made if you talk about lambda I of A transpose. So the same thing would exactly hold if you talk about sigma I square of A is also equal to lambda I of A transpose. In this case, I would be again be equal to 1 to R, and for the rest it would be 0 actually. So I hope the connection between singular values and eigenvalues is clear. And with that, we conclude our discussion of basic linear algebra. And in the next video, we will start with convex sets.